Good morning, guys. Hope all are doing well. So yesterday I told you all to see this graphical interpretation of a given function. So here basically the given function is f1 is equal to x square, f2 is given as 2 to the power x, f3 is a polynomial, and f4 is equal to x cube. So when you see and you draw the graph of f1, f2, f3, they look like this. Okay, I just drawn the graph here. So this is for your F1, this is for F2, and this is for F3, and this is for F4. So clearly, depending on the horizontal lines which intersect the graph, okay, so we will decide whether it is on one or not, on two or not. Okay, so here basically in given function F1, so if I draw a line, horizontal line, so here you can see that it is intersecting any horizontal line. If I take here, so it will intersect at two different points. Okay, so the same thing I've written. The graph of these functions appear in this figure. We can observe that the horizontal lines which intersect the graph of f1 twice, and there are horizontal lines which do not intersect a graph f1. So here if I consider, because my function is from here to here if I consider the horizontal line at the base, so which will touch the graph, but it is not intersecting the graph. So I have the horizontal line which is both intersecting here, and also I have a graph which is not intersecting at all. If such conditions you have, then it is neither 1, 1 nor on 2. Okay, and also you can observe. So f1 of x is equal to x square, they have said. If I consider x1 is equal to 1, also I'll get 1, the answer will be 1. If I take x is equal to minus 1, then also the answer will be equal to 1. That means both 1 also will go to 1 and minus 1 also will go to 1. That implies it is not 1, 1. It is not 1, 1. Similarly, if you see it is a real valued function r to r if I have considered, and if you take this all the elements here in the real numbers r, here also you take all the real numbers. Whatever the real numbers you are taking, only positive real numbers will be having the image. That means here the negative real numbers will not be having any images here. Thus it is not onto. Are you observing, guys?
Yes, ma'am.
Okay, so this is the, I mean, like we can say theoretically, but even geometrically also, since the horizontal line is intersecting this particular graph at two different points, and also we get some horizontal line which will not intersect at all. If such cases, we can decide that it is neither 1, 1 nor on 2. Okay, then again same thing when you do it for 2 to the power x. Okay, so you just take here x is equal to say 1, it is 2. If x is equal to say 0, you take, it is 1. If x is equal to minus 1, you take, what will happen, guys? 2 to the power minus 1, that is nothing but what? 1 upon 2. Again, it is a positive number. So what basically is happening? So basically, we are getting what? We are getting the positive number or negative number for any values which we are giving input.
Positive.
So what about the negative images? If I have the real valued function, then is that negative images are having any impact here? I mean, negative images are having any pre-image in the x? No. Correct? So,
Yes, ma'am.
yeah. So that is our theoretical part. So hence F2, it is 1, 1. 1, 1 means every element is having an image, unique image, different image I have. But it is not onto. It's not, okay. You please mention this as not onto. Why not onto? Because negative elements are not having any images, pre-images in the x. Following, guys?
Yes, ma'am.
Okay. Similarly, come to the F3. You take any function here. So this, if you just draw the graph, it looks like this. The third graph which you're observing here, like this. So here, every element in your codomain will be having a pre-image. Okay, that means every element will be having the pre-image, means it is onto, but it is not 1, 1. Sometimes you are having same image for two different elements. I mean, like one element will go to two different images. So like that will not be 1, 1. There will be no unique image. So just you check for what it is not going to happen, how it is not 1, 1. You can just substitute the values and you can check. Okay, so this is how F3 also fails to be 1, 1, but it is on 2. And similarly, come to F4, guys. If I take positive value, it will take positive. If I take negative value, it will take negative. Correct? If I take x is equal to 1, it will be 1. If I take x is equal to minus 1, it is minus 1. That means both positive value and negative values will be taken care of. And it is having from, anyways, it is going from, the set A to set B. So every set of elements A is having the unique image, and also element of this set B is having the image in the A. That means it is both 1, 1 as well as on 2 function. Okay, so hence, and moreover, when you draw the horizontal line, right, it has to intersect at one single point. Then only we say that is 1, 1 function. And when you draw the vertical line, then also we should get only one, at one particular single intersection. Then only we can say it as on 2. Okay, so that's the basic idea. Okay, so please remember. So this is how even geometrically we can interpret 1, 1 and on 2 function. Am I clear up to this, guys? H section people? H section sleeping? H section people? G section?
Yes, yes, ma'am.
Okay.
Yes, ma'am.
Okay. So now let's go on to some examples. So here state whether or not each diagram defines a function from A to B or not. So quickly, guys, just tell me. So here I have one diagram, say A to B. So whether is it a function or not? Quick. Is it a function?
A is not a function.
A is not a function. Why?
Ma'am, B to C, B element is not assigned with anything.
Very good. So B element is not assigned with any element of this B. Okay, good. So what about this particular function, guys? Is it a function? Here every element is assigned. Is it a function?
No, ma'am, but they are assigned with multiple.
C is assigned with multiple images, correct? So C is
Yes,
going
ma'am.
to X and C is also going to Z. That is not allowed in the function. So hence it is also not a function. What about this?
Yes, ma'am. This is a function.
It's a function.
This is the function because different elements are assigned with different elements, and moreover, A elements are completely assigned with the images. Okay, so hence it is a function. So hope you are understanding. So now, guys, this is for you. Practice the practice problem. You have to sketch and you have to check whether the graph of the function is 1, 1 onto or not. Okay, just check this. Now let's see. If the function f is from A to B, g is from B to C, defined by this figure. So they ask us to find the composition, guys. That is, g is a function. The composition of f and g. We will read it as f and g, but we will write it as g dot f. Okay. So please remember the composition of f and g is given by A to C. Okay. So they're asking us to find out this. So let's draw this diagram. Whatever is we are having here, you can observe. This is my function f from A to B. This is our function g from B to C. Okay, so here you can see that it is given A is going to Y and B is going to X and C is going to Y. So this is given. And g is a function, that is X is going to S, Z is going to R and Y is going to T. Now by the definition of the composition function, we know that the composition of, say for example, g dot f of A. This is nothing but g of f of A. So what is my f of A? You just check where A is going to. A is going to Y. So that is nothing but g of Y. So g of Y means where Y is going. Y is going to T. That is equal to T. So this is our g of f of A. So for first element implies A is going to T. Next, similarly, we want g dot f of B, which is equal to g of f of B. What is g of f of B, guys? Where B is going? It is going to X. So that is g of X. So g of X means where X is going to? It is going to S. Following?
Yes, ma'am.
Okay, similarly, just check what is g of f of C. G of f of C, which is equal to C is going to Y. So therefore, it is g of Y. So where y is going to? Is going to t. Okay, that means your g of f of a, the composition function of a is t, whereas b is yes and c is t. So how the direction is? That implies a is going to y is going to t, then b is going to x, then x is mapping to s, c is going to y is in turn mapping to t. So this is the relation. Are you following? So this is your composition function now, okay? Let's see. Let the function f is from a to b, g is from this, and h is from c to d. This is defined by this diagram. To determine each function is onto, find the composition function of h dot g dot f. So just try the first one, guys. Don't see the, answer. Just see, I'll explain you the function f from a to b. This is your a, this is your b, c, and d. Just check whether a to b is 1 1 and onto or not. They are checking about onto, whether it is onto. A to b, guys, is it onto function? Onto means what?
No, ma'am.
Element of B, all the element of B must have the images here, pre-images. Is there three, this element 3 is having the pre-image?
No,
So what it is then?
it's not onto function.
It's not a onto function, correct? So here f from A to B is not a onto function. So what we should say, 3 belongs to B is not the image of any element in A. That's the reason. What about G function, guys? G from B to C, is it onto function?
No, ma'am.
Yes,
Yes. This Z,
Also
is it
Z.
having any image?
no, ma'am.
Okay. So therefore, hence G from B to C is not a onto function. What about H, guys?
H is also not onto. Phi does not have image.
Correct?
Yes.
Z is equal to, I think it has to go to 5 somewhere. Let me see whether I have done any mistake. Okay, if 5 is not having the image, then it is not onto. If suppose Z is going to 5, then it is onto. Okay, so let me check this. So here I have written onto means it has to go to 5 somewhere like this. Okay, anyways, so thus you understood that now this is not onto. Second one is find the composition function of this h dot g dot f. How do you do that? So now you have to check your A is going to 2 and 2 is going to X. X is going to what? Where X is going to, guys? Are you following? Your A is going to 1. Sorry, A is going to 2. And your 2 is going to what? X. And X where it is going?
4.
It's going to 4. That means you are having the relation from A to 4. This is your relation. Next again, B to 1, 1 to Y, Y to 6. So directly I'll write B to 6. Then C to 2, 2 to X, X to 4. So that is C to 4. Are you following, guys?
Yes, ma'am.
Okay, so like this you have to have a relation. So here you think here you should have 4. Okay, so like this is the composition of h dot g dot f. Okay, so like this, whether they'll give you 3 number of functions or they give you 4 number of functions, any number of functions, you can have the composition. If it is well defined with the diagram, it is more clear. Okay, so this is the B part which they asked you. I think some practice problems I have given you here. You try those examples. Now here you come. If f is a function from R to R be defined by this, then now f is 1 to 1 and on to. Hence f has the inverse function f inverse. So they asked us to find the formula for F inverse. They are mentioning everything. They told that it is 1 1 and it is also onto. When it is 1 1 plus onto is there, that implies it has to have what? Inverse. So hence we have to find out the formula for inverse. So let's find out. So y be the image of x under the function. So what we do? We consider y is equal to f of x, which is given as 2x minus 3. 2x minus 3. Consequently, this x will be the image of y under the inverse, that is f inverse. So solving this above equation in terms of y, you will be getting the value. So that implies, so here you have y is equal to 2x minus 3. So if you write everything in terms of y, that will be your inverse. So if I take minus 3 on this side, it becomes y plus 3. So 2x is equal to y plus 3. Or if I take x only, then it is y plus 3 by 2. So this will be your inverse. So if a function is in terms of y, so y is in terms of x, then it is just a function. When you take x in terms of y, then it is your inverse function. That's simple. Okay. So like that you have to convert the given problem. Followed, guys?
Yes, ma'am.
Okay. So now let's come to the next simple concept we have. Something like sequence, something like indexed classes. So all that we will just see the definitions and bit examples. Okay. So here as examination point of view, 1 1 on 2 and inverse functions, that part you will be having more focus. So here whatever these are, the next concept which I am going to deal with now, it is just the supportive concept for the next parameters which you are going to learn. Okay. So here I think you have studied already the sequences in your classes, if I'm not wrong. What is a sequence, guys? Basically, is it not a function again?
Ma'am, it is a function which has a specific pattern, ma'am.
Yeah, it may be having a specific pattern, but from where it will start? It is actually the sequence is, it is a function from the set of natural numbers. Natural numbers, or you can also call them as the positive integers, into any given set A. So basically we are dealing with function, but the function has to be specifically from the natural number set to any given set A. So this is very important, and this is any set. So this function or a mapping or a relation, we call it as a sequence. So usually we denote our sequence by an, or also we can say we can sometimes denote it by an like this, or sometimes we denote it as an such that n is coming from the natural set. Okay, so these all are the notations. Sometimes we can also write it as a1, a2, a3 up to an. So these all are the notations. Okay, and it is nothing but it is the image. It is the image under what we are getting. Okay, so similarly, if suppose you are having, what is the sequence then? Sequence is the function whose domain is a natural number and it goes to any set A. And we can denote it by either this, or we can also denote it by this. Now, a finite sequence, and there is infinite sequence, because we deal with both. So finite sequence means if it is containing finite number of elements. A sequence or a function which is having the finite mappings or a finite number of relation, say 1, 2 up to m. This is having the finite number of elements, where m is any finite number. From this set to say A, if I have a relation, then it is the finite sequence. Usually we denote it as A1 to AM, or we can also denote it as AM such that m belongs to n. Okay, so where m is a finite number, it may be 4, it may be 5, it may be 100, it may be 1000, but it is a finite number. Okay, and such finite sequences, sometimes we call them as list. If you guys remember, in the Python you will be using a list, or you will be using even tuples. From where this concept of tuple and list is coming? From this DMS. Are you able to connect, guys?
Yes, ma'am.
Okay, so this is a finite number of sequence. The finite sequence we call it as a list, or we also call it as m tuple, where m is the specified number. So for example, if I have the sequence like say 1, 1 comma 2, 1 comma 3, 1 comma 4, and so on. If you see, if you observe carefully, it is following some pattern. Correct? So how do I write? If I generally I want to write this, I can write this as an is equal to 1 by n. If I put n is equal to 1, I'll get the first term. If I take n is equal to 2, I will get second term, and so on. I'll be getting the different terms. So similarly, if I have this sequence 1, 1 by 2, 1 by 4, 1 by 8, so it is in general, I can take the sequence Bn as, say, 1 by 2 to the power n, or also can be written as 2 to the power minus n. So if I put n is equal to 0, I will get the first number. If I put n is equal to 1, it is 1 by 2. If I take n is equal to 2, it is 1 by 4, and so on and continued. So more specifically, these are actually regularly used your sequences. You'll be using them unknowingly. So these are all what their sequences. So in the first sequence, if you observe, where your n is begin with n is equal to 1, whereas in the second sequence your n is taking n is equal to 0. So sometimes we include here in the natural number set, we also include 0, 0, 1, 2, and so on, continuous. That means sometimes for some sequences we also require 0. Hence we may take n union 0, that is whole number set. Okay, that also can be considered. Am I clear up to this point, guys?
Yes.
G section,
G section. Yes.
H section. Following, guys? Okay. Now see the important sequence. Usually we see the sequence repeatedly, and this is a very important sequence in the convergence level. When you study the complex analysis and all in deep, we will have these sequences many. We will be using it widely. Okay, and even in the like say fuzzy logic and all, we'll just work with 0 and 1, and we will always play in this sequence. So what is the importance of this sequence? It is formally defined as an is equal to minus 1 to the power n plus 1. It is in general. If I take n is equal to 0, it is simply minus 1 to the power 1. 0 plus 1 is 1, that is minus 1. If I take minus 1 to the power 1, so minus 1 to the power 1 means 1 plus 1, it is 2. Minus 1 to the power 2 is again 1 plus 1. So either it is minus 1 plus 1, minus 1 plus 1, or it is 1 minus 1, 1 minus 1. It is repeating only these two entities. So either you can write it in this way, where you can start your n is equal to 1, or equivalently you can write it in this way, where you can start your n is equal to 0. If you start it with n is equal to 0, you can again you will get this same sequence. Okay, so this is another sequence, important sequence, where you will be writing it generally like this, or you can also write like this. If you're writing like this, you can start with n is equal to 1. If you're starting like this, you can start with n is equal to 0. Okay, so this is another example. Now see, suppose a set A, it is finite, and capital A, it is viewed as the character set. Say for example in alphabet, then the finite sequence over A is called as string. I think you heard about this word also. Are you using string? In Python, will you be using string, right?
Yes, ma'am.
So, or it is also called as what? Well, anything if you write in terms of word, it is called as string. Correct? So, when you're defining it, so if suppose the given set is in terms of finite characters, it is viewed as a characters, then we call it as an alphabet. Or we can, maybe in terms of alphabets you're talking about, then that finite sequence we call it as string, or we also can call it as a word. Okay, and it is usually written in the form of A1, A2 up to AM. That is without a parenthesis. We are not using any parenthesis. Are you using parenthesis for string, guys?
No, ma'am. No.
Okay, so please try to connect Python, what you are studying, and here the theory. Okay, so you can see how whatever the connections you're able to see in the Python, I mean whatever the code you're trying to write there, for that the basic tools we are providing. That's how mathematics you can connect. You go to any programming, you just build any model as such, but what is important is, guys, how exactly that has been exhibited is by mathematics. The base is mathematics. So that's the reason I'm telling you, don't try to by heart the stuff, try to understand and analyze what is behind. So you will love it. Okay. So this is one more thing which we are, I mean, like now you can see the list you have seen, the tuples you have seen, and the string you have seen, which you can connect now. Okay. So now the number of m of characters in the string is called as what? In the string, the number of characters, what do we call it as? Is it not is called as length?
Yes, ma'am.
Same thing here. Okay. No need of by-hearting, just if you are good enough in Python, so you can understand the concept. Whatever the characters you are dealing with in the string, suppose you have 100 characters, you have 200 characters, so that all thing we call in the technological language as length. Okay. One also waves a set of the 0 characters. So for example, or you can say the nil character. If there is no character at all in the string, it is called as what? Null string or empty string. Okay. So if there is no character at all, then we call it as empty string or the null string. Okay. Then we can add, we can write as the sum of, suppose you have the numbers, you have the sequences, the infinite sequences which you want to sum up. How do we go with? We can use the summation symbol, that is this. We can read as sigma. So if you're considering the sequence A1, A2, A3 up to so on, then the sum of these sequences, if I say have up to n number of elements, then we can write it as summation of, say, Aj, where my j is running from 1 to n. You can see it is going from 1 to n. We can write it in a short way. So it is a sum. We use the summation symbol. Okay. Or if suppose this is your sequence, we are starting from m to n, we can write it as simply summation of Aj, where my j is starting from m to n. Are you observing, guys?
Yes, ma'am.
Okay, and this j, we call it as, this expression of j, we call it as dummy variable or dummy index. So you can use anything like I, you can use k, you can use any alphabet you can use. Just specifically, I'm using j. I think you have heard about dummy variable also. Are you following, guys? So please try to connect it. Okay, so this is the dummy variable which we can use, and we can denote the sum of the given sequence. Okay, so for example, you are having, say, summation of ai bi, where I is running from 1 to n they have given. So first it will take I as 1 for both the elements a1 b1. Next it will go switch to 2, then it is a2 b2. Next it will switch to 3, up to what it will go, up to an bn. So this is one example. So summation of j square, where j is equal to 2 to 5. So j square you have. So j square means a variable here is j. So in place of j, you can see it is starting from 2 to 5. But it is in the form of square. So it is 2 square plus 3 square plus 4 square plus 5 square. Are you following, guys?
Yes, ma'am.
Okay, so that is the sum it will give you. So if you just try to write the Python programming, there also you will get this idea. Then summation of j, where j is running from 1 to n. So that means it is from 1 to n, the sum of all the elements I am interested in. So it is basically n into n plus 1 by 2. So this is the answer. Okay. So here, these are all the example for the summations. How do we sum up the sequence? So here, something called induced class of sets. So just the definition is required. So you here what exactly we have is, we have a set I, which is a non-empty set. So there should not be it should not be a null set. It should have some elements. Then let S be the collection of sets and indexing function from I to S. So there is a non-empty set I, and there is a collection of a set S. So such collections I will be taking this as I. So what I will do here is, I have a function f from this set I to S. Okay, that is this function. Such a way that for any I belongs to I. So if I consider any element from this which is belongs to I, we denote the image, that is f of I, okay, by AI. So you can see indexing, I'm indexing that element. So it is a basic function. So here whatever element you have, say I is coming from this element, or you can say A if I am taking from this element, the image will be f of A. So instead of writing this as f of A, I will write this as AI. So this AI implies this is coming from the set I. This is called as indexing. So thus the indexing function f, it is usually denoted by, you can see AI, such that where this I is coming from, this I is coming from the set I. So this we call it as indexing. Sometimes we can also denote simply as AI. Okay, sometimes we denote it as AI such that, here you can write this as such that I is coming from I. So these all are the notations. Okay, so what is basic meaning is, there is a non-empty set from where to the set, collection of a set there is a function. I want to write this images, instead of writing it as the images, I will denote them as the indexing. AI, I may write it as BI, I may write it as CI, anything. So like that, which I am denoting, this we call it as indexed classes of set. Okay, then this set I is called as indexing set, and the element of I are called as indices. So whatever the elements now we have got, this AI and all, this we call it as indexing sets, and whatever the elements belongs to this I. So I may be having 10 elements, 20 elements, 100 elements, they are called as indices. So here you can see, this is your indices, and this is whole set is indexing set. Okay, if f is 1 1 and on to, we say that s is indexed to I, sorry, s is indexed by I. Whatever the function you are defining here, if the function is both 1 1 as well as on to, then we say that this collection of set is indexed by the given set I. Okay, just it is a notation, just remember how do we note it. Okay, and here you can see at I be the set of z integers. Z means it is both positive and as well as negative integers you have. For each integer n, we assign the following subset. So say for example, I have the an. So you can observe, this is the indexing set where n such that x is such that x should be less than or equal to n. X is less than or equal to n means, suppose your n is 3 here. Here if you have a3, that means x is such that your x should be less than or equal to 3. That is the collection. X is less than or equal to 3 means on the integer it will start from minus infinity to what? N. N means 3, so it is up, it will go up to 3. Are you observing?
Yes, ma'am.
Okay, so this is your indexed set. This, instead of writing all this, if I write a3 and if I write it is on set of integers, that is understood that it is the same set. That's how indexing the set will reduce the work. Instead of informing everything, we just inform, we just tell that it is a3 or a4, depending on that you're going to write the equations. I think time is up, guys. So if you have any questions, let me know. Any questions anybody has, let me know. Is it clear, guys? All of you?
Yes.
Okay, let me stop the recording.